Imagine the scene in June 2026. Without warning, critical production environments across several global regions began throwing persistent HTTP 403 forbidden errors. The culprit wasn't a server outage or a botched deployment. It was the immediate enforcement of the Export Control Directive 2026b. Anthropic's flagship Fable 5 and Mythos 5 models, the engines powering your automated customer logic and RAG pipelines were suddenly geofenced. For years, architects prioritized API performance and token costs, but in a single midnight update, the API-first strategy became a single point of total failure. This wasn't just a technical bug, it was the weaponization of the AI supply chain. We are seeing the death of the borderless AI era, where high-performance weights are now treated as strategic national assets, subject to the same restrictions as nuclear technology. By the end of this lecture, you will understand how to re-engineer your stack to ensure that a single diplomatic shift doesn't delete your entire business logic overnight. In the world of enterprise IT, we often treat SLAs as ironclad guarantees. However, the Fable 5 crisis proves that geopolitical risk sits above any commercial agreement. When a government classifies an AI model as dual-use technology, your service contract with a provider like Anthropic or OpenAI essentially becomes void in restricted zones. Most architects built their 2024 and 2025 roadmaps on the assumption of infinite, low-latency access to frontier models. This dependency debt has now come due. If your business logic resides exclusively in a prompt behind a foreign API, you don't own your product. You are merely renting it at the pleasure of a foreign regulator. We must move beyond simple API consumption toward a framework of service continuity that accounts for the sudden disappearance of a primary provider. But how can we achieve this without sacrificing the state-of-the-art capabilities that only frontier models provide? The answer lies in the fundamental shift from API-first to sovereignty-first architecture. To survive the 2026 landscape, architects must embrace architectural resilience. This isn't just about high availability or multi-region cloud setups. It's about model sovereignty. This means having the ability to swap a restricted model like Mythos 5 with a local, fine-tuned Llama 4 or a regional alternative within minutes, not months. We are looking at a future of model diversification, where the orchestration layer dynamically routes requests based not just on cost and latency, but on geopolitical compliance scores. This lecture is designed to be your survival guide. We will transition from fragile, single-provider dependencies to a resilient, multi-provider framework that leverages hybrid deployments combining frontier APIs with hardened, on-premise open-source models. But wait, is it actually possible to maintain Fable 5-level performance on local infrastructure? The answer depends entirely on your data strategy and how you handle the next level of governance. In the next 30 minutes, we will deep dive into the 2026 AI governance matrix. We'll move beyond the hype and look at the actual mechanics of how export controls are triggered based on TFLOPs, model parameters, and training data origins. You will walk away with a decision matrix that helps you evaluate whether to buy, build, or hybridize your AI capabilities based on the latest risk profiles. We will analyze the supply chain from the GPU level up to the application layer. By the end of this session, you won't just be reacting to the Fable 5 blackout, you will be the architect who predicted it and protected your organization's core assets. This is the new standard for IT governance, where geopolitical foresight is as critical as your CI/CD pipeline. But before we build the defense, we must understand the enemy. Let's look closer at the specific technical triggers that make a model like Fable 5 a target for international control. In the world of high-stakes IT governance, the mental model of export has shifted fundamentally. Traditionally, export administration regulations, or EAR, focused on tangible hardware, think high-end GPUs or semiconductor manufacturing equipment. However, the 2026 regulations surrounding models like Fable 5 have expanded the definition of dual-use technology to include specific computational thresholds and model weights. We're no longer just tracking crates at a port, we are tracking tokens across a network. If a model exceeds a certain FLOPS training density or parameter count, it is legally classified as a controlled commodity. This means the act of providing an API response to a restricted region is legally equivalent to shipping a physical weapon. For architects, this transforms AI from a simple software dependency into a regulated strategic asset with severe compliance overhead. But how do they actually enforce this when the model stays on a server in Virginia? The answer lies in the legal definition of access control as an export mechanism. The complexity intensifies when we look at how the US government enforces jurisdiction over intangible exports. Under the 2026 framework, the location of the server is secondary to the identity of the person receiving the output. This is the foreign person rule applied to AI. Even if your Fable 5 instance is running in a safe zone like North Virginia, if the inference result is transmitted to a user in a restricted jurisdiction, an export has occurred. This requires cloud providers and model owners to implement jurisdictional fencing. This isn't just simple IP blocking anymore. It involves deep packet inspection and identity verification at the point of authentication. The process starts at the API gateway, moves through an identity provider, IDP, with residency checks, and ends with a compliance log that must be auditable by federal agencies. This means your global architecture is now fragmented by invisible legal borders that override your technical topology. But wait, does your global cloud contract actually protect you from these sudden blocks? A common misconception among enterprise architects is that using a global cloud provider like AWS or Google Cloud provides a layer of protection or legal abstraction. In reality, the compliance burden has shifted directly onto the consumer of the API. This brings us to AI KYC, Know Your Customer for AI. Much like the banking sector, AI providers in 2026 are mandated to report usage patterns that might suggest model distillation or proxy access by restricted entities. This isn't a theory, it's a reporting requirement with massive fines for non-compliance. Many organizations assume that their enterprise agreements guarantee availability, but every one of those contracts contains a compliance with laws clause that allows the provider to sever access instantly without liability if federal export mandates change. You are not just managing an API, you are managing a legal relationship with a sovereign power. You might wonder, if this is so complex, why didn't Anthropic just use better filters instead of a total blackout? The next section reveals the brutal reality of their decision. When the Fable 5 export mandates were updated in 2026, Anthropic faced an impossible technical hurdle: attribution difficulty. The foreign person rule is binary: either you are compliant or you are not. However, telemetry showed that sophisticated users were using multi-hop VPNs, residential proxies, and synthetic identities to mask their origin. For a company like Anthropic, the risk of a single high-profile leak to a restricted military entity outweighed the revenue from entire regions. They realized that their identity verification systems were not geopolitically proof. This led to the preemptive shutdown. Instead of attempting granular identity verification that would likely fail an audit, they pulled the plug on all questionable jurisdictions simultaneously. This is the ultimate risk management move. When the cost of a false positive, a leak, is company ending, you accept 100% of false negatives, service denial. This choice highlights a critical flaw in modern AI architecture. It lacks a partial compliance mode. The Fable 5 blackout didn't just affect direct users, it triggered a massive supply chain ripple. Consider an enterprise that uses a CRM with an integrated AI assistant powered by Anthropic's API. When Anthropic blocked access, that CRM's functionality died instantly for thousands of employees worldwide. This is the downstream impact of centralized AI models. Many of these integrations were built using cloud marketplaces or third-party wrappers like LangChain, which lacked robust error handling for geopolitical 4-3s. We call this contractual force majeure. The suddenness of the event meant that failover strategies, if they existed, couldn't be triggered because the primary wasn't just slow, it was legally vanished. This ripple effect exposed how deeply Fable 5 had been woven into the enterprise fabric without any AI sovereignty or model redundancy plans. This isn't just a technical outage, it's a supply chain collapse. Is this just a one-time event, or is it a repeat of history? To truly understand the 2026 Fable 5 crisis, we must compare it to the GPU bans of 2022. Back then, the strategy was hardware containment, preventing the physical shipment of silicon. It was slow, and bypasses were common through third-party resellers. Fable 5 represents software-defined containment. It is instant, centralized, and absolute. In the 2020s, you could still run a model if you had the hardware. In 2026, if you rely on a closed-source API like Fable 5 or Mythos 5, you own nothing but a temporary right to access. This event proves that the open source vs. closed debate is no longer about cost or performance, it's about survival. Organizations that invested in model portability or on-premise deployments of open weights, Llama 4, remained operational, while those on the pure SaaS path were left in the dark. This historical evolution shows that AI containment has moved from the factory floor to the data center backbone. This leads us to a disturbing realization about our current architectures, which we will dissect in the next chapter. Many architects mistake API interoperability for true model portability. When you integrate a model like Fable 5, you aren't just calling a function. You are embedding proprietary prompt structures and model-specific fine-tuned adapters into your core business logic. Experienced developers know that a prompt optimized for Fable 5's reasoning engine rarely produces identical results on a fallback model like Llama 3 or Mythos 4. This is the proprietary prompting moat. Furthermore, if you've deployed LoRa adapters specifically trained on Fable 5's internal weights, those ATs become worthless the moment an export control goes into effect. The cost of rewriting every system prompt and retraining every adapter across a 500-service microarchitecture is not a weekend task, it is a catastrophic project failure. We are seeing a new form of vendor lock-in that is much stickier than the cloud database locks of the previous decade. If the brain of your application is swapped overnight, the entire nervous system begins to reject the new organ. But wait, is it just the model itself that fails, or is the entire operational pipeline at risk? Let's look at the operational fragility of the modern AI stack. We often rely on the Salem myth, the belief that a 99.9% to availability contract protects us from geopolitical interference. In reality, export controls operate outside the jurisdiction of standard service-level agreements. When a state-level export ban hits, the API failure cascades instantly through your RA pipelines and autonomous agents. Imagine your vector database retrieving context for an insurance claim, but the reasoning agent responsible for the final decision is a hard-coded Fable 5 endpoint that now returns a 403 forbidden error. The failure isn't isolated. It's a systemic collapse. Your customer-facing interfaces begin hallucinating or timing out because the middle-tier intelligence layer has vanished. Mapping these hidden dependencies reveals that most modern AI architectures are built as a house of cards, where one single point of failure in Washington or Brussels can darken data centers in Seoul or Tokyo. But what happens when the model is available, but the data it needs is legally restricted from moving? Let's look at the conflict of data residency next. Data gravity and sovereignty are now in direct conflict with AI model availability. Enterprises often face a sovereignty paradox. Their data must remain within national borders to comply with local regulations, yet the highest performing models like Fable 5 are hosted in specific geopolitical cloud regions, primarily US West 2 or East 1. If export controls restrict access to these specific regions, you are forced to choose between using an inferior local model or risking regulatory noncompliance by routing data through gray zone proxies. This isn't just about latency, it's about the legal jurisdiction of your inference calls. In the field, we see firms struggling to maintain AI residency, the ability to keep both the data and the compute within a sovereign boundary. When the export control wall goes up, your high-performance AI strategy effectively hits a border patrol checkpoint. The friction created by these borders can degrade your competitive edge overnight. Now we understand the structural traps. How do we actually measure the business cost of these vulnerabilities when they inevitably fail? In traditional disaster recovery, we talk about RTO and RPO, recovery time objective and recovery point objectives. But in the era of AI export controls, we must define intelligence, RTO. If Fable 5 is cut off, how long does it take your engineering team to retarget, reprompt, and revalidate your entire service catalog on a fallback model? For a major enterprise, a 24-hour outage of an AI-driven customer support agent can result in millions in lost opportunity costs and brand erosion. If the recovery time is 1 week, the business impact transitions from operational hiccup to existential threat. We must evaluate the cost of manual intervention during these outages. Are your fallback systems ready to take the load, or will you be forced to revert to expensive human-in-the-loop processes that you've already downsized? This framework is essential for every CTO to present to the board. But calculating the time is only half the battle. We must also quantify the IQ drop that occurs when we switch models. How much smarter is Fable 5 than your backup plan? When forced to move from Fable 5 to a suboptimal, compliant fallback model, your application experiences an IQ drop. This isn't just a minor performance dip. It's a degradation in reasoning, coding capability, and nuanced understanding. If your system depends on Fable 5's ability to handle complex multi-step reasoning, and your fallback model is a smaller 7B parameter local model, your success rate on complex tasks might drop from 95% to 60%. This gap, the benchmark erosion, leads to increased hallucinations and customer frustration. For an automated legal review system or a medical diagnostic tool, this drop is unacceptable. You need to visualize this gap now, before the crisis hits, so you can determine which features will need to be disabled or restricted in safe mode. If you don't know the delta between your primary and secondary models, you are flying blind into a storm. This brings us to a critical realization. Why did we make it so hard to switch models in the first place? It's time to address the hard coding problem. The most dangerous technical debt in the AI era is the hard-coded endpoint. In my experience auditing enterprise architectures, I see developers hard-coding specific model strings like Fable 5 Ultra V1 directly into their microservices. This is the Y2K bug of our generation. When the export control is enacted, these systems don't just slow down, they hard crash. Legacy technical debt in AI isn't about old code. It's about rigid dependencies on external intelligence that you do not own. We need to shift toward an AI gateway pattern, where model routing is handled by a dynamic governance layer, not hard-coded into a YAML file or a Python script. If your architecture requires a code deployment to change a model version, you have already lost the battle for resilience. We must treat models as interchangeable commodities, even if their performance differs. As we've seen, current architectures are too brittle for the 2026 geopolitical reality. So, how do we rebuild? In the next chapter, we will introduce the sovereign AI governance framework, your blueprint for true architectural independence. In the world of 2026, relying on a single AI provider's API is no longer just a technical risk, it is a violation of fiduciary duty. We must implement what I call the sovereign AI abstraction layer. As an architect, your primary goal is to decouple the business logic from the underlying model provider. This middleware layer acts as a buffer, ensuring that if a specific model like Fable 5 becomes unavailable due to export controls, your application remains agnostic to the change. This isn't just about clean code, it's about survival. By standardizing input-output schemas at the gateway level, we ensure portability across different jurisdictions. Think of it as the Kubernetes for LLMs, abstracting the infrastructure so the application can run anywhere. But here is the critical question. How do we design this stack to handle both high-performance needs and emergency resilience simultaneously? A resilient 2026 AI strategy requires a multi-model active-active-active configuration. We categorize our stack into primary and secondary tiers. Your primary models, typically top-tier US-based SOTA models like Fable 5, handle complex reasoning and high-value tasks. However, you must simultaneously run secondary models, which are often open-weight variants like Llama 4 or locally developed sovereign models, in an active-active or hot standby mode. We've seen in recent field tests that organizations without this dual pathing face total service paralysis the moment an API key is revoked due to regional restrictions. By routing a percentage of non-critical traffic to your secondary stack, you maintain warm infrastructure and verified prompt compatibility at all times. But can open source models really match the reasoning power of the giants in a private environment? The export control crisis has revived the case for the private data center. For years, the industry pushed toward cloud first, but we now realize that the cloud is just someone else's computer under someone else's laws. Hosting open-weight models like Llama 4 or high-performance local variants on-premise provides a strategic hedge. If the US government pulls the plug on Fable 5 exports to your region, your on-premise cluster becomes your primary production environment. This hybrid approach allows you to leverage the cost efficiency of SaaS during peacetime while maintaining the operational continuity of on-premise during geopolitical conflict. We must move from cloud-first to sovereignty-first architecture. However, governance isn't just about hardware. What are the actual standards we need to enforce on our procurement teams? To wrap up our principles, let's look at the 4 pillars of AI governance for 2026. First, visibility. You cannot manage what you cannot see. Every API call must be logged and audited. Second, portability, mandating that all prompt engineering and RAG pipelines are model agnostic. Third, compliance, ensuring that local data stays within local borders, especially as international AI regulations diverge. Finally, continuity, having a pre-verified plan B for every critical AI-driven business process. Your procurement standards must now include an export control clause, demanding that vendors provide clear roadmaps for regional availability. Theory ends here. Let's look at the actual code and dynamic proxy architecture that makes this failover possible. In the implementation phase, we apply the dynamic proxy design pattern. This isn't just a simple load balancer. It's an intelligent router that understands model health and regional availability. When a prompt is submitted, the proxy evaluates the destination. If the primary US-based endpoint returns a 403 forbidden or 429 limit exceeded common indicators of sudden policy shifts, or export blocks, the proxy immediately reroutes the request to a local instance or a neutral region provider. This happens in milliseconds, transparently to the end user. This layer also handles logging and credential rotation across multiple providers. Routing is the easy part, but what about the syntax? Different models expect different formats, and we need a way to normalize them. Prompt normalization is the secret sauce of portability. Anthropic, OpenAI, and Meta all use slightly different structures for system messages and role-based chat history. If your prompt is hard-coded for Fable 5, it will fail or hallucinate when sent to a local Llama 4 instance. We use a template standardization approach where the developer writes a universal prompt, and our abstraction layer transforms it into the specific XML, JSON, or ChatML format required by the target model. This ensures that your few-shot examples and system instructions remain functional regardless of the backend. If a model starts failing, we can't wait for manual switch. How do we automate the detection of a geopolitical blockade? Automation is the key to resilience. We implement automated circuit breakers that specifically look for error codes associated with API restrictions. In the event of a geopolitical kill switch where multiple providers in a specific region go offline, the system triggers a global failover to the sovereign instance. This isn't just an NFL statement. It's a state machine that monitors latency spikes and failure rates. If the 95th percentile latency of Fable 5 exceeds a threshold, we assume a throttling event and shift 50% of the load. This prevents a complete service outage. High availability sounds expensive, though. How do we justify the cost of running 2 infrastructures at once? Finally, we must manage the insurance premium of this architecture. Running a dual model system is inherently more expensive than a single provider setup, but we optimize this through token management and tiering. We route low sensitivity, low complexity tasks to cheaper local models by default, saving the expensive sovereign-ready SOTA models only for critical reasoning. This hybrid cost model often results in lower total costs than a native SaaS-only approach, while providing the necessary risk hedge. In the next chapter, we will turn this architectural theory into a concrete, tactical 3-step action plan you can implement starting tomorrow. The clock is ticking toward the 2026 deadline. Are you ready? The moment export controls like those for Fable 5 are announced, the clock starts ticking. The first failure point in most enterprises isn't the technology itself, but the lack of visibility into where that technology is actually embedded. We often see shadow AI where individual teams have integrated high-end APIs into internal tools without central oversight. You must perform an immediate inventory audit. This isn't just about checking your primary cloud billing. It involves scanning your code repositories for hard-coded API endpoints, auditing CI/CD environment variables, and reviewing third-party SaaS tools that might be using Fable 5 as their backend engine. Without a comprehensive AI bill of materials or IBOM, you are flying blind into a regulatory storm. We need to identify every touchpoint where regulated models are currently driving value. But identifying where the model is used is only half the battle. Where it's hosted is where the legal hammer actually falls. Once the inventory is clear, we must map these assets to their geopolitical realities. In the world of 2026, the cloud is no longer a borderless utopia. You need to assess the risk profile of your vendors based on their corporate headquarters and their physical infrastructure locations. If your primary AI provider is headquartered in a nation enforcing these export controls, they are legally bound to cut your access regardless of your local contract. We analyze geopolitical exposure by looking at 3 layers: where the model was trained, where the inference hardware sits, and the jurisdiction of the company holding the keys. Even a model hosted in a neutral region can be deactivated if the controlling software is subject to an export ban. This mind map helps architects visualize the fragility of their current vendor stack. This approach reveals a hard truth. Even if your vendor is compliant today, how does their performance compare to the alternatives we might be forced to use tomorrow? The final step of our risk assessment is the gap analysis. We must acknowledge that Fable 5 represents the top tier of reasoning capabilities. If we are forced to migrate to a regional model or a smaller open-source alternative like a fine-tuned Llama 4 or a local sovereign model, what exactly do we lose? We measure this in terms of reasoning depth, context window size, and latency. For example, if your customer support bot requires a 128K context window to process manuals, but your Plan B model only supports 32K, your architecture will break. We use a structured table to compare current high-end models against compliance-safe alternatives. This allows stakeholders to see the functional degradation and plan for mitigations, such as implementing more complex RAG, retrieval-augmented generation, pipelines to compensate for smaller model context. Analysis alone won't save your production environment. You need physical infrastructure capable of hosting the alternative. Resilience in 2026 is measured by your ability to host your own compliance baseline. This means building or securing a stack that you own completely from the silicon up to the inference engine. We are seeing a massive shift back to local inference for critical services. This stack starts with a secure GPU procurement strategy, ensuring you have enough H100 or B200 equivalents within your own data centers or sovereign cloud providers. Of the hardware, we deploy an orchestration layer using Kubernetes combined with high-performance inference servers like VLLM or NVIDIA Triton. This setup acts as your Plan B baseline. It doesn't need to be as fast as Fable 5, but it must be fully operational when the external APIs go dark. This layered approach ensures that even if the global network is fragmented, your core intelligence remains online. Having the hardware is great, but can your team actually pull the plug and keep the lights on without a manual? The most sophisticated architecture is useless if the failover fails during a crisis. That is why we recommend AI blackout drills. Just as we perform fire drills or disaster recovery tests for databases, we must now simulate the sudden loss of Tier 1 AI models. In these drills, we programmatically trigger a failure of the Fable 5 API and observe the system's reaction. Does the AI gateway automatically route traffic to the local compliance baseline? Is the output quality still within the acceptable threshold for production? These drills ensure that your CI/CD pipelines are ready to redeploy services with fallback model configurations in minutes, not days. We move from reactive panic to proactive resilience through continuous evaluation. This tactical resilience is your survival kit for 2026, but the final verdict on your architectural legacy is yet to come. In the final chapter, I will give you my verdict on the future of the AI architect in this age of fragmentation. As we approach 2026, the fundamental evaluation criteria for AI systems have shifted drastically. For the past few years, IT leaders were obsessed with raw performance metrics, latency, token throughput, and MMLU scores. However, the Fable 5 export control crisis has shattered this narrow perspective. We are now entering the era of the performance compliance resilience triad. An architect who builds an ultra-fast system that can be shut down by a sudden regulatory change is no longer an asset. They are a liability. You must evaluate your AI stack based on sovereign AI principles. Can this model run in a disconnected environment? Is the weight file locally hosted? Can the inference engine bypass foreign cloud dependencies? These are the questions that will define corporate survival in the mid-2020s. We must move beyond simple API integrations and master the art of local fine-tuning and secure orchestration. In this new landscape, the resilience quotient becomes the primary KPI for any mission-critical national infrastructure or enterprise system. But how do we actually transform this high-level strategy into daily architectural decisions? This brings us to the ultimate verdict for the 2026 AI landscape. Throughout many years in the field, I have seen many technologies come and go, but the politicization of the AI supply chain is a unique paradigm shift. The role of the IT architect has evolved from being a simple system builder to a risk-aware strategist. We can no longer treat AI models like Fable 5 as mere commodities that will always be available through a stable global market. Instead, we must treat them as strategic assets that require robust governance, backup contingency plans, and a deep understanding of international compliance. In 2026, the best AI architect isn't necessarily the one who can craft the most elegant prompt or choose the model with the highest benchmark. It is the one who designs a system that remains operational even when the external world says no. As you close this lecture, remember that your career growth now depends on your ability to bridge the gap between cutting-edge innovation and rigorous risk management. This completes our deep dive into the Fable 5 export controls, but the journey of building truly resilient AI systems has just begun.